Hi guys. All right, day 5, testing for dependence and independence using the product test. So yesterday we saw that we could check for independence by using this formula right here, right? If the probability of A given B is equal to the probability of A, that's where we compare the two decimal values. If they're equal to each other, then they're independent. If they're D different, then they're dependent. Sorry for the noise, but my daughter's been making lunch every single day for me while I do these videos. So she's noisily making lunch. Stop making so much noise. Oh my goodness, sorry guys. All right, so I want to show you a different test. So and it stems from this one. So watch. We know that the probability of A given B can be changed over to the probability of A. Oh goodness, let's start writing that over again. Okay, so we know that the probability of A given B can be written as probability of A and B, right, divided by the probability of B. Well, if I take that formula and I place this over 1 and I cross multiply, right, probability of A and B, and I set it equal to the product of the two, isn't that a true sentence? So here's where another test comes into play, and it's just an alternative that you can use to prove if something is independent or dependent. And here's the formula. It's the probability of A and B is equal to the probability of A times the probability of B. So most of my students love to use this one, unless you're forced. Sometimes we're forced into using this one that we did yesterday, but if you're not forced into it, this is always what kids prefer. And we use this to find if something's independent or dependent. Okay, so what I'm going to do is I'm going to take a question from yesterday, and we're going to do it both ways. So we're going to do it using what I taught you yesterday, which is the conditional. And then we'll use today's formula, and you'll see that both of them work. Okay, so let's do a little practice from yesterday on the left, and then we'll use today's new rule, and we'll see how either one of them can be used. All right, it says, given the table on gender and sports are being female and preferring soccer independent events. Now, it doesn't matter if I ask you if they're independent or dependent. You're just going to do either test you want, but I'm going to do both tests right now. And remember, order doesn't matter either. Here I'm choosing to do probability of female given soccer. You could start out with soccer given female, but once you choose, now it has to go every other. Female, soccer, female, FSF. It has to go in that order once you choose what you're going to do. Okay, so let's change this over. Let's change this to the probability, right, of female and soccer divided by the probability of soccer, and we'll set that equal to the probability of female. I'm going to just get myself a little bit more room. Okay, so probability of female and soccer. So female and soccer is right here. That's 15, right? And my total for everything is 50. So 15 over 50 divided by probability of soccer. So here's soccer, total soccer is 25 out of how much? 50. And then I set that equal to the probability of female. So here's female, go all the way down, and it's 30 out of 50. Okay, now it's your job to turn each side into a decimal. So do your top bottom side on the left, turn that into a decimal. We get 0.6. Now do your right hand side, turn it into a decimal, 0.6. And now we can see that they're the same. Same, therefore independent. And that's my answer. Remember, D different, D dependent. So if they're the same, they're independent. Okay, so watch. Remember, and the decimals are not your answer. The decimals are your work. Because if I had chosen to do probability of soccer given female, I would have got different decimals, but they would have still worked out to be in the same decimal. Okay, so let's try the new way now. And again, most kids like this new way. It's called the product rule. So if I want to, we're doing female and soccer again. All right, so the product rule is the probability of A and B is equal to the probability of A times the probability of B. This is just a test to see if they're independent or dependent. This is not like a formula that we use in any other situation. This is just to test for independence. So probability, and you can do whatever one you want. I'll do female and soccer. You can write it as soccer and female. And what's nice about this one is order doesn't matter either way. So this is usually the preferred formula the kids like. All right, probability, let's erase all of this stuff up here so I can recircle things. Okay, so let's get a pretty color. So let's do whoopsie. Okay, so probability of female and soccer. So female and soccer is right here. So 15 out of 50 equals probability of female, 30 out of 50, times the probability of soccer, 25 out of 50. And then just use your calculator, guys. Do the left-hand side in your calculator. What do you get? You get 0.3. Put the right-hand side in. What do you get? 0.3. Notice that that is not my answer. 0.3 is not my answer. My answer is that they're the same, therefore independent. So what does it mean to be independent anyway? It means they don't affect each other. So it doesn't matter if you're a girl or a guy and what your favorite sport is. Okay, so hopefully you understand here that I'm pretty much doing the same lesson as yesterday, independent, dependent. I'm just showing you another way that you can check for it. Okay, so I think today we'll try to use this new formula. And again, both kids, like usually kids love this one. All right, we're going to skip 2. And we're going to go on to 3 because I don't want to do 10,000 questions with you. Now, I started to write some stuff in just to save some time and try to write a little neater for you. Okay, so let's read what number 3 says. Given events A and B such that the probability of A is 0.6, probability of B is 0.5, and then I'm reminding you from day 1, the probability of A union B. This guy right here is the OR symbol. Union is OR. Easy way to remember it because remember, the intersection symbol, the upside down U, can be turned into an A, which is AND. Okay? All right, so I took all the information, I put it off here to the side, and I want to determine whether they are, here it is, independent or dependent. Okay, so here's my problem, right? I gave you guys like this new formula today to do, right? I said the probability of A and B, is that equal to the probability of A times the probability of B, right? That's the new one I wanted to use today instead of doing the conditional formula. But look, I don't have and, right? I don't have that. So they gave me or. And even if I tried to use yesterday's formula, you still need and. So if they give you or, you need to go up and you need to use the OR formula from day 1. And if I use the OR formula from day 1, won't I be able to find out and? So all we do is plug in our information. So, oh, whoa, didn't mean to do that one. Let's get rid of that. Okay, so let's plug in. OR is 0.8. Probability of A is 0.6. Probability of B is 0.5. And I want to find and. Once I find and, I can come down below and I can do my work. All right, so let's just do a little bit of basic math here. You can just use your calculator. So we're left with 0.8 equals 1.1 minus x. And we did stuff like this on day 1. Subtract 1.1, subtract 1.1, and we're left with 0.3, well, technically negative, equals negative x. So 0.3 divide through by a negative, so 0.3 equals x. Okay, and what was x? That was my probability of A and B. So now come on over here. Probability of A and B equal to the probability of A times the probability of B. And let's see if we get the same answer. So we wind up with 0.3 equals 0.3. So we can say that they're the same, therefore independent. I ran out of room. Okay? It's as simple as that. Now, if you had done the conditional formula, you would get the same answer as well. Not the 0.3s maybe, but you would get decimals that were the same. Thank you, honey. Okay, let's see. Okay, next, I took out some of the information for you as well. Okay. So we got 12% of U.S. homes own a Mac computer. So notice that I converted, right, to a decimal. 72% have at least 2 flat screen TVs. If the 2 events are independent, what is the probability of owning a Mac and at least 2 flat screens? So look, they're telling me that they're independent. If they tell me they're independent, then both of the formulas are actually true. So the conditional formula is true and the product rule. But hopefully you're seeing that the product rule is going to be way easier here to use. They're telling me that this is a true sentence because they're saying that they're independent. So we're just going to sub in. So I want to know what this is equal to. Well, it's going to be equal to 0.12 times 0.72 because they're telling me it's independent. They're not asking me to prove it. They're saying, hey, these are independent. So there's my decimal. Convert to a percentage. And the one that's closest is choice 1. Okay, it's a little different there. They're telling me that they're independent. Okay, 5. Okay, so I chose to put some, use the space above because there's a lot going on here. All right, let's read. Sean's team has a baseball game tomorrow. He pitches 50%, so you can see that I converted up above to a decimal. There's a 40% chance of rain during the game tomorrow. If the probability that it rains given Sean pitches, probability that it rains given Sean pitches is 0.4. It can be concluded that these 2 events are. Okay, you remember doing this question? My daughter says she remembers doing this question when she was prepping for the Regents in her year. Okay, it can be concluded that. So look, I see independent, dependent, so I'm thinking about my formulas, but let's just talk about this new word. Oh, and complements, remember that's the one where it adds to 100% or one whole, but mutually exclusive. I just want to tell you what that means. So mutually exclusive means that they can't happen at the same time. So like if I'm driving, I can't make a left turn and a right turn at the same time. That would be an example of mutually exclusive events. Or if I toss a coin, it can't land on heads and tails at the same time. So those would be mutually exclusive. So, I mean, can't he pitch and it rains? Those could both happen at the same time. They're not exclusive. So we can get rid of choice 3. And I don't know, I don't really see anything going on with complements here. But let's decide which formula we want to use. Okay, so look, I'm going to write down both formulas. So there's 2 formulas to prove independence and dependence. So we can do the probability of A given B is equal to the probability of A, every other. Okay, sorry, getting distracted by my daughter washing dishes. Kayla's that. I can use this formula, which would make me have to turn this into probability of, well, actually, we wouldn't even have to turn it into, hold on right there. Or I could use this formula, probability of A and B equal to the probability of A times the probability of B. Okay, so look, if I look at both of these formulas and look at the information that I have, do we see how you have this? Oops, I meant to highlight that. Do you see how you have this information right here? So we can just go up and we don't even have to convert that formula. Just plug it right in. Right here, 0.4, right? Equals, but we have to change these letters over. So we'll make this R. and we'll make this one pitch, and then this one would be R. So make sure you do that. Okay, I like to start out with the A's and B's, but then you should put in the correct ones. I hope you can read that okay. Okay, and it's every other. So now probability of rain is 0.4. So see how we wouldn't want to use this formula because we don't even know and. So we would straight up use the conditional one. So they came out to be the same, so therefore independent. Okay, that's a little tougher. They forced me into using the conditional formula on that one. So that's why we do need to know both of them. Okay, next. Just redo that one if you need to. Next, I took the information out again. And let's see. So it says the probability that Gary and Jane have a child with blue eyes is 0.25. You can see I put it all down here. The probability that they have a child with blonde hair is 0.5. The probability that they have a child with both blue eyes and blonde hair, right? So that's both right here. That's my and. Is 0.125. Given this information, the events blue eyes and blonde hair are. So look, there's the words again, independent, dependent. So we know we have to do a test. Mutually exclusive? Is it not possible to have blonde hair and blue eyes at the same time? It is. So this guy's gone. That's not going to be one of the correct ones. So right away I can get rid of 3 and 4 because choice 3 is in there. All right, so it's either independent or dependent. So which formula do we want to use? We can use either one here, but I'm thinking let's use the product rule. So probability in A and B is equal to the probability of A times the probability of B. And now we'll just sub in, and is both. 0.125 equals 0.25 times 0.5. You know, and you can go above and put, you know, blue, blonde. Oh, see, they make this so hard because it's like the same spelling. Okay, so blue and blonde. Blue and blonde. You can put them right above. All right, so let's see what we got. 0.125 equals 0.125. All right, so what do we know? They're the same, therefore independent. So this would be this guy working. So it would be choice 2 only. All right, hopefully that went well for you. And that's a typical, you know, Regents question. All right, so we got 2 left. 7 and 8. 7, there's a little mistake there. That should say R. Okay. If 2 events, A and B, are independent, then the probability of A and B is equal to. Well, isn't that the formula? If they're independent, that's the product rule. Probability of A and B is equal to the product of A times B. So choice 2. That is the product rule. So they're telling me they're independent. And then we got one last one. It's a little harder, but let's just try it anyway. If events A and B are independent, okay, so let's just come down here for 1 second. If they are independent, then I know both rules are true. The probability of A given B is equal to the probability of A. I know that this is true. And I also know that the probability of A and B is equal to this guy. So I know those are both true sentences. There's no test to be done. I know that both of them are true. So they're saying which of the following is not necessarily true. All right, so let's go through our choices. All right, so probability of A times B is equal to the probability of A and B. Well, that's this formula right here, so that's definitely true. Also, I see this one. Probability of A given B is equal to the probability of A, right? That's this one. That's true too. I could tell right away. Do you guys see it right here that this one is totally not true? How can that be true? They're not doing every other. It's BAA. We can't go in that order. It has to be every other. If this one could only be true if it was BAB. Oopsie. If it was BAB. That's the only way that could be true. So how the heck is this one true? Over here, number 2. Why is number 2 true? Well, you know we've been doing this all year, right? Put this over 1 and cross multiply. I get the probability of B given A is equal to the probability of B. So this guy is definitely true. So the only thing that's false, just answer that and tell her I'm busy, honey, would be choice 4.
Hi, Eddie. It's Kayla.
Okay.
My mom is doing one of the
All right, sorry for the distractions here today. All right, so that's it, guys. We're not going to do the remaining 2. Hopefully you understand that. Really important stuff. I'm proud of you for doing the best that you can, so keep working hard. All right, bye.